Another type of reaction that goes through a three-membered ring intermediate is the formation of epoxides. This one, the three-membered ring intermediate, really is actually the final product, and that is the oxygen that's in a three-membered ring. So it's an oxygen that's attached to two other carbons in that three-membered ring. So it is an ether, but because it's in the three-membered ring, we call that an epoxide. These can be made from treating an alkene with what we call peroxy acid. So the peroxy acid is basically like a carboxylic acid would be with just an extra oxygen stuck in there. So instead of RCO2H, which would be a carboxylic acid, this is RCO3H. So there's just an extra oxygen. There's that oxygen-oxygen bond in there. And so the general structure is given here. A couple of specific examples, there's peroxyacetic acid. So acetic acid would just be without one of these oxygens, so it would just be an OH there. We have an extra oxygen, so it's peroxyacetic acid, and then metachloroperbenzoic acid is another one. We're going to learn about that meta term and what exactly that refers to. It's basically just the distance those groups are apart on that benzene ring, but we'll talk more about that in the next chapter. This one, basically, for these purposes, we're just going to put this as an R group and then use the rest of the molecule. So for the mechanism of this reaction, we are going to have this epoxide form on one side of the molecule. So just like with our other three-membered rings, we do have to make sure that we're forming that ring just on one side of the molecule. And in this case, our arrow pushing is going to be just a few more arrows than what we had seen before. So what's going to happen is the oxygen that's attached to the hydrogen, this is the one that's going to be attacked by the double bond. So it's going to come and attack that oxygen. The reason for that is that oxygen-oxygen bond is actually pretty weak. And so once that gets attacked, the bond and the electrons from between the two oxygens can go straight into making a double bond to that carbon, which is going to push these pi electrons out through the oxygen and then attack that hydrogen. And then the electrons from between the hydrogen and the oxygen will go down to the oxygen and attack back. So this is the shortcut mechanism. There are a few other arrows we could have shown and gone from lone pairs to say specifically what was going to happen, but this one cuts down the amount of arrows we have to draw for this particular reaction. So what does this all mean? Well, really the only thing that's actually getting deposited onto the molecule is this oxygen here. It's getting attacked, and then these electrons are coming back to make another bond. So there's actually going to be two bonds to this oxygen, one from this carbon and one from that carbon. These bonds are going to be on the same side. Let's just choose to also make this oxygen coming out of the page. We could also have chosen to make it going back into the page. So we're going to have that as our product, and we're also going to have a carboxylic acid left over. This isn't going to be our main product, but it is going to be one of our products that are just, it's a byproduct of this reaction. So let's trace where all of the electrons were going, because this is a pretty complicated few arrows that we drew there. So if we trace where everything's going, we can say we have the bond in red is the pi bond. That is going to make one of the bonds to the oxygen. So that's where those electrons went to making that sigma bond. We are also, so kind of our next arrow is breaking the bonds in between the two oxygens. So we can show that one in blue. So that bond ends up becoming one of the pi bonds of that carbonyl in the carboxylic acid byproduct. And then we had broken this bond with the other arrow, so that we're going to show in green what happens to those electrons. We can say, well, those ones are the ones to the H here. And then the other electrons that were important for the mechanism were coming from that bond between the H and the oxygen, and that's going to actually be the other bond to the ring. And so that all happens all at the same time, and that's going to give us our epoxide. So this one is a three-membered ring intermediate, but is also stable enough to actually be isolated. So what we're going to talk about for opening up these epoxides, that's going to be a separate video. We can actually take this epoxide and we can put it into another reaction. So we can isolate it and then put it in. And that's not what we could have done with the bromination and the oxymercuration reactions. So this where this one is a little bit more unique. So in the next video, we'll talk about the opening, which is going to look very similar to how the bromonium was opened up and how the mercury cation was opened up in the oxymercuration.